Hi, everyone. I'm glad to see you all here this morning. It's my pleasure to introduce Mohamad Aziz, a postdoctoral researcher in my research group, in addition to working with Hussein Sourem at Quebec and Professor Hanan Begdougi from the math department, the math and industrial engineering department. Mohamad has earned his PhD from McGill. Sorry, Polytechnic. Oh, really? Master's from. Oh, sorry. I'm so sorry. So his PhD from Polytechnic and his master from McGill. And today he'll be talking about his recent work, bridging the gap between Graphon mean field theory and energy trading. So, Mohamad, the floor is all yours.
Thank you, Anton, for the introduction. So as Anton mentioned, today I'll be discussing the optimal energy trading in residential prosumer clusters via Graphon mean field game theory. This is under joint work with Professor Hanan Begdougi, Antoine, and Dr. Hussein Supreme from Iraq. So briefly, I'll go through the outline of the presentation. First, I'll be talking about the motivation and the context of the problem that we're trying to solve. Then I'm gonna go briefly through the literature review on the methodologies that we are using for solving the optimization problem. Then I'm gonna go into the details of how we are formulating the problem and how we are solving the problem via Graphon mean field game theory. And then I'll conclude the presentation and how this work can be extended in for future work. So we all have heard the term smart grid, but what does it actually mean? So smart grid refers to the inclusion of recent advances in information communication and control technologies into the energy grid in order to attain increased connectivity, automation, coordination, and sustainability. Just like before, I forgot. So it's an informal presentation. So whenever you guys have a question, just raise your hand and state your question. As the same for the online people. Just raise the hand and Professor Antoine will say the question out loud. So here we have so many stuff that are trying to coordinate and work with each other. And the whole goal is to reach some sort of automation and better coordination in order to attain sustainability. The ultimate goal from all this, the ultimate goal is to diverge from the centralized energy system that is known from generation, transmission, distribution to the end user to a more decentralized energy grid where we have different components cooperating and participating with each other. And the notion of unidirectionality will have to change to be able to cooperate the bidirectionality of the power flow. However, this will lead to an increased complexity as we are integrating more and more DERs, and the increase of DERs necessitate a more efficient and flexible energy mechanism. In addition, the notion that we are typically dealing with a consumer who will be changing toward a prosumer due to the deployment of DERs at the level of consumers. That all these forces us to have a better energy management in order to reach reliability and better efficiency in integrating all the components that will help us to move toward a decentralized energy system. So in nutshells, the opportunity from moving toward a decentralized energy grid, deploying smart grid potentials, is the reduction of operation cost due to the fact that we can delay capital cost, and it will be more environmentally friendly as we are using more and more renewable energy resources. In addition, when we deal with a decentralized system, one of its pros is that we reach a more resilient and reliable improvement because we're not relying on one source. We can manage with our local supply. The challenges that we face when we're dealing with renewable energy resources or prosumer in general is the notion of non-dispatch generation, because in this the generation that comes from renewables are not robust. They are stochastic depending on the conditions and everything. In addition, that we are enabling demand side management and DERs at each node, which leads to a more flexibility in terms of load and generation. And all these are interacting at the same time. So we are moving toward a multi-energy system with so many components interacting. And the whole goal is to have a better coordination between all the participating entities to achieve the better integration. So, of course, I'm not gonna, my work doesn't go globally on the whole picture. My work focused on generally on prosumer households and how and the idea of residential community of prosumers. So my work in the PhD focused on a cluster of residential prosumers that are connected through each other through what we call the cluster aggregator. In this approach, we are still assuming that we have grid connection. So that's why we are relaxing the term microgrid to residential prosumer cluster. However, like the approach can still function in both cases, in grid and in grid connection and in grid disconnection. So the approach here was to find the optimal interactions that lead to an equilibrium within our cluster. That was so the equilibrium was in the control and the equilibrium price. And the question was like, why did we focus on residential prosumer cluster? So if we are able to kind of find the optimal interaction with prosumer cluster, this led us to lower costs in terms of the energy bill by optimizing local DERs and by finding the optimal interactions, we were able to reach a lower energy bill for the participating households. In addition, we were able to help the grid provider in their mission for and during peak period. And the idea when we are deploying DERs, it ultimately lead to more cleaner energy that can be used for the local demand. And if in case we are in surplus, we can use this surplus of clean energy for the entire grid. Another advantage of a prosumer cluster is the idea that we discussed earlier, that it can help us to reach a more resilient and secure system. As we all know, like sometimes like we have a weather condition, some lines will drop. So how we can reach resiliency is like by using our local resources to better manage our needs in our cluster. And the question that we asked after that is like, is this concept can be replicable to cover like a larger kind of residential network, and that's one of the motivation behind my current work as a postdoc, where we are considering this kind of architecture for the energy grid, where we have not just like one residential cluster that we are trying to find the optimal energy trading in it. Here we are having a cluster of clusters where we are trying to kind of partition the residential network into clusters of clusters, and we're trying to find the optimal local interactions between the prosumer in one cluster, and how the cluster of cluster can optimally exchange energy between each other. We still having the grid as our kind of last resource for balancing the load. So everything is still in our approach is still assumed to be to be having the possibility to still be functioning in grid connection mode. Any questions so far? Yes.
So just from my understanding, here you're trying to partition the distribution network, but is it feeder per, like, maybe I'm thinking more too much physically, but
Yes.
do you partition like feeder per feeder, or do you look at the entire network from the station?
So how the technical aspect of the grid we're trying to have, like you have like the substation that is connected to so many buses. Let's assume like the aggregator is at bus 1 and you have so many houses that are connected to this bus. So the aggregator can be seen as the bus in that sense. And we're trying to find the optimal interaction within our cluster. So at this node, we were able to estimate how much in aggregate, how much we'll have in and out from that bus.
Okay. What's the H variable?
Which H? Oh, house. Oh, the definitions will come later, sorry. But this is just like the architecture for the COC. So here this diagram kind of represents the interaction that we will be trying to model. Each house in a decentralized way will try to find their optimal control strategies for their appliances. We're assuming all the houses to be smart houses. By smart houses, we mean they have rooftop solar panels, they have their energy storage system. Each house has their EV, which can be in grid connected mode and charging and discharging. And the whole approach is to try to find the optimal control for these houses when we are trying to estimate the local effect and the global effect of the COC. So here, the difference between one cluster to a cluster of cluster that as a house, you're not just playing with the people around you or like your local neighborhood, you're as well interacting with the COC. Now I'm gonna go through the methodologies that we're adopting to find our optimal solutions. We're trying to formulate this problem using game theory as it provides us with formal, analytical, and framework with a set of mathematical tools to study complex interaction among rational players. In this sense, we are assuming that each household is a rational player, and by rational player, it is like you're trying to always do your best response. So you have one goal, which is like minimizing your energy bill, and your best response is what are the set of controls that we're trying to find in order to minimize our cost function, which is the energy bill. In my previous work in one cluster, mean field was the methodology that we adopted to use to find the equilibrium interaction. Mean field game theory is a branch in game theory which focuses on dynamical game with large number of stochastic agents. Each agent is interacting with the mass effect. So if you go back to the cluster, one cluster that is connected to the grid, the house is only affected by how the global or the aggregate cluster is functioning, rather than that's the only thing that is affecting their cost function and dynamics. And that's why we were able to use the results from a mean field game theory to find our optimal trading in the residential cluster. Each house is seen in a sense that they are minor. Considering a large number of cluster, one house does not affect the aggregate, because like if you're considering like if the 200, 300 house cluster, one house does not have any impact on the aggregate. However, the aggregate have a significant impact on the house. And that was the motivation behind using mean field and the residential cluster. So in a high level, mean field game theory study the existence of Nash equilibria between individual agents and the mass in the infinite population limit, where individual strategies of each agent is found in the sense of best response, and the collective set of strategies reflect the mass effect or the mean effect. And then we kind of exploit the relationship between the infinite problem to the finite problem by finding what is defined in mean field game theory as the epsilon Nash equilibrium. So you solve the problem for the infinite population, and then you try to find the epsilon Nash for the finite population problem. But now, since we are dealing with a bigger network where you have so many local aggregate and you have a global aggregate, is there an extension to mean field which can handle such a network? And the answer that we found is that we try to investigate this problem by Graphon mean field game theory, which is an extension of mean field game theory to analyze dynamical game on large and complex network. It provide a framework for analyzing decentralized control of agent on large network and simplifies the analysis of complex network games while working on Graphon limit theory, where each agent decisions is affected by a local mean effect and a global mean effect. In the sense of the COC, the local mean effect is your cluster, and the global mean effect is the COC interactions. It has the same concept that each agent is trying to find their best response, reacting to two main mean effects, the local and global. So Graphon mean field theory help us to study dynamical networks where local nodes possess intrinsic states that evolve as a result of interaction with other nodes. Back to the COC, your cost function is affected by whatever is happening in your local neighborhood and on your global graph. It also accounts for different kind of behavior where you are either influenced freely or influenced by a local influence or global influence. In addition, the theory can be applied on large networks of nodes where complex connections that can be either assumed dense and sparse. In our framework, the first work that we started is like considering a dense network, and we're trying to extend this framework to a more sparse network. And the whole premises of Graphon mean field theory is it's super robust when it comes to the size of population. As the population size grows in terms of computational and everything, it's still almost comparable to so like the more you increase the bigger the number of nodes is, the computation does not grow with the size of population rather than with kind of the randomness and the interactions that in the graph. And now I'm gonna start by presenting our problem formulation. Here we can see the smart house. So this is H. Each house is having a solar rooftop. They have their energy storage system. They have their set of demand-side management, which are represented by the controllable load and the shiftable load, and the EV, which can be either charging mode or discharging mode, similar to the energy storage system, which can be charging or discharging. Here we just need to mention that the flow of power is first you have your solar generation, and then it's used directly to the load, and then with the surplus from your solar panel generation, you either can store it or sell it. So first we need the load, and the net of that energy, we can decide either to store or sell. So the house energy management is the aim of it is to find the optimal control strategies for the appliances connected to it, and the EV can be connected or on the road. So the HAM, the house energy management system, kind of know the schedule of your EV. So those are the system variables. We have the base load denoted by YB, controllable load by YC, shiftable load by YS, and the total load is the summation. We have the solar generation, we have the energy battery system. And here we need to mention when we denoting HIK, the ith home in the kth cluster. And the set of controllable variables are the controllable load, the switching time for the shiftable load, the charging and discharging for your EV battery, and the charging and discharging for your energy storage system. This is how we modeled the solar generation, where we denoted the PPV to be the generated power. The generated energy from the solar panel is derived through the following equation. Do we have laser here? And the Brownian motion kind of that has laser. No, so too late now. And the Brownian motion, or the linear process, kind of sums all the noises that happens in the performance of your solar panels. For the load, which is divided into three types, you have base load, controllable load, shiftable load. In our framework, we assume the base load to be first order differentiable, and we're denoting the first derivative of the base load by Zi. The controllable load is defined is modeled by the increment stochastic differential equation, where UC is your control decision, PC is kind of the rated power for your controllable load. So if you assume your HVAC system, it's kind of like how much it will take to go from one temperature to another temperature. Similarly, the shiftable load is modeled via the equation shown here, and here PS is your rated power for the shiftable appliances. So if you have a washer or dryer, PS is the rated power for the cycle of operation. This equation shows the total load at time t. And now for the EV. As I mentioned earlier, the EV it has two modes of connection. Either can be on road, where the people living in the house are using the EV in the trip, or when it's on connected mode. When it's in connected mode, the dynamics of the state of energy is modeled via the following equation, where RE is the discharge, gamma E is the charge, and the Brownian motion just kind of sums all the performances of the EV. The charging and discharging are formatted via the following equation, where eta E represent the efficiency in charging and discharging. PE to G is the rated power for charging and discharging from either to grid to E to the EV, or from EV to the grid. For the ESS, the energy storage system, similar to the EV state of charge, the state of charge for the ESS is dynamics is shown in the following equation, where RS is the discharge energy, gamma E is the charge energy. As I mentioned earlier, how the power is flowing in the house. You have the solar panel. The first thing that goes in the generation is to your load. So we have to define the delta term here, which represent kind of the net of your solar generation after meeting your demand. If it's positive, if we have a surplus, we either can set this control to be positive, in a way that we are charging from our surplus, or we can directly set it to be as a supply. And in case of a shortage, we still we can either charge or use our battery to meet our demand, and that's how RS is modeled. So, no questions so far? So far, so good. So each house have their set of demand and has their set of supply, and the net energy at each house is denoted by C of I, and those is just like the linear combination between your load and your potential generations. So RE, RS are the discharge, gamma E, gamma S are the charge. And if we replace all the previous equation, this equation shows you how your net energy will evolve in time.
So not homogeneous system, each house has its own coefficients.
So that's a good question. The first approach we use, we're assuming all houses are uniform, but we can still expand to a heterogeneous system.
What's the I index?
So the I index is that's like the general form. Right?
You address the one.
Yes.
Okay.
But yes, so the complexity of the approach vary with considering uniform to non-uniform, because he would be studying it with like considering the case of homogeneous agent to heterogeneous agent, the complexity differs. But and so far, like we and the current work that we submitted is just we assumed uniform houses. So all the technical parameters in the appliances are the same. So if you want to consider it in a case like our cluster is like one developer built bunch of houses, they deployed the same appliances. That's our appliances. That's our kind of reasoning for using uniform agents.
So the homogeneity for now is on the cluster level?
On the appliances level.
All the grids?
Yes. And the cost function is defined by the L function, where here we have the three parts. So we either can meet our net energy through our local exchange, which we anchor PRPC as our price, or we can get from the COC, where the price we anchor is PCOC, or we can still have the grid as our balance, and the price of the grid provider is denoted in PG. Or represent the maintenance and operation cost for the DERs, which are your solar panel and your battery, either EV or DSS. W1 plus W2 plus W3 equals 0 to make sure that we have a balance. PRPC is our local price, PCOC is our global price, and PG is the grid provider. So the HAM's objective is to try to find the optimal control to minimize the following cost function. By estimating the local and global prices denoted by PRPC and PCOC. Now I'm gonna go through the graph representation of the grid. Here we are gonna represent the COC by the graph G, where we have our set of nodes, our set of edges, and our weight function. And the set that the nodes are partitioned into clusters. Each cluster have their aggregator denoted by AJ, where we are having M clusters and N number of nodes. How we model the interaction between between the nodes is by using the electric distance as the weight measure between the nodes, which is so in an intuitive word, the electrical distance represent how strongly these two nodes are influencing each other. So if we have a node I and a node J, the EIJ represent how much of the energy available at node J is seen at node I. And then we derive the Graphon kernel from the energy distance. In our approach, we assume that in our cluster, we don't lose energy. So houses in the same cluster so the same amount of energy available at house I to house J is the same amount of that can be transferred or traded between the houses. So we don't assume any kind of lossless intra-cluster exchange. For the cluster of cluster, we kind of model the system in a way that we are trading all the energy at our aggregator node, and the energy distance or the weight between a node I and cluster K to a node I and K prime is the same as the electric distance between the aggregator and cluster K to the aggregator and cluster K prime. The state space for each node X are the solar generation, base load, controllable load, shiftable load, your charge and discharge for the EV, for the ESS and the EV. And based on the previous equation, we can write the stochastic differential equation for the state of space in this format, where F is represented the drift and is based on the previous kind of modeling for each state space. Here we need to note that the probability distribution for the state space X is denoted by the mu function, which kind of summarizes the probability density function for all the parameters in the system. How we find the global and the local exchange price is by finding the local aggregate and the global aggregate, and then using the P-lock as our mapping from the local aggregate to the equilibrium price, and the P globe from our global aggregate as seen at the node X to PCOC.
Okay, it's showing where the price is the equation.
Cost function.
Okay.
And the cost to go function VETX is shown in this following equation, where we're trying to minimize the cost to go as we go from t to the final time t. This is what? This is C or delta. So this is the terminal cost fee, capital fee is. So we need to have like our Lebanese character, not just like Greek characters. And the HGB equation following the cost to go function is derived in the following equation. So to find the optimal controls, we have to found in the following equation. So in the simple words, like you set your control your controllable load to be -1 if by increasing your controllable demand, the cost function is increased, your control action is -1, and vice versa for the rest. So this is how we find the optimal controls for that minimize the HGB equation shown here. And for the propagation of the probability density function, this is the FPK equation. The whole kind of in high level, the whole objective from our work is to try to find the fixed point for operator tau, where the operator tau is you have your probability density function, which generate the optimal control, and you're trying to find the fixed point between your probability density function and your optimal controls. So the goal is to establish the existence and uniqueness of a fixed point solution, mu star, u star, where mu star is the density function and u star is the optimal controls for the house energy management system. Those are the necessary assumptions that are needed for the existence and uniqueness. We need the drift and the cost function to be elliptical and continuous in x and u, the control set to be convex and compact, the graphon to be symmetric and bounded between 0 and 1, and the pricing functions to be elliptical and continuous. The graphon monotonicity assumption is crucial for the uniqueness. So what graphon monotonicity assumption means, like if we have a measure that is leading to a higher consumption, it automatically will lead to a higher cost. We were able to kind of provide the existence and uniqueness solution for our tau. For the full details, we're happy to say that it's available in GERAD, and this work is submitted to PSCC. We were able to find the existence and uniqueness of the fixed point mapping for the operator tau, and we were able to find the epsilon Nash equilibrium for the finite COC.
Okay, so now for given prices, you have a bit of this, but you are still not controlling the price.
Yeah.
You give the prices.
You don't give the price, you estimate the price. So the HAMS has the statistical information. He has the understanding of the COC topology, and based on that, he is estimating the equilibrium prices. And based on this estimate, he's finding their optimal controls.
Okay, as a house,
and
see the prices. What's the equation that I need to solve to find the optimal value?
So this is your cost function.
As a house.
Yes.
Okay.
And you're trying to minimize the cost to go function.
This is at the grid money.
There's no grid management. Like, we're trying to solve it in a decentralized way. So each house energy management system is solving this these equations.
The grid at the grid level, I find the equilibrium and assign prices, then send the prices to houses. Houses will take these prices as information, and based on the prices, they will have their decision on whether to produce or charge.
Yeah, that's like in the sense of like you have a centralized player where he is the one generating the prices. The whole premises of this work is to be able to do it from a decentralized way where we reach a Nash equilibrium. So there is no communication needed. The system, if all the houses are participating, are applying those kind of sets of control, those are the set of equilibrium that we will see. So we are trying, as a HAMS, we're trying to predict the aggregate effect, and based on our prediction, we're trying to find our optimal controls. Now I'm going to go through the numerical simulations, and this graph kind of represent the diagram for the operator for the fixed point operator. Here we have our mu, which gonna give us our aggregate mean effect. We feed it back to our cost function, and we find our optimal control. So the algorithms aim to find a fixed point solution for this loop. This diagram kind of represents what the humps in each house is doing. So we observe our states, we estimate the aggregate effect, we find our optimal control. This might give you a better idea. So we don't have like a centralized formulation. It's a decentralized way where your humps is trying to, and this is the step-by-step algorithm. We start by an initialization. We find our aggregate effect. We solve the backward Hamiltonian Jacobian Bellman equation, and then we find the optimal control. We feed the optimal control to solve the forward Fokker-Planck equation. We get a new realization of the probability density function. And if we reach convergence, we exit, and this is our mu. We tested this approach on a cluster of cluster formed by 100 RPC with 200 uniform prosumers. Back to your question, uniform prosumers. The electric distance was calculated from the admittance matrix from the following reference. Those are the sets of technical parameters that we used for the controllable load, for the shiftable load, for the rated power, for the ESS, and the EV. And this was the convergent distribution at the end of the simulation. So this is the convergent mu. And these are the equilibrium prices for the local and COC. We assume the grid provider is Hydro-Quebec, and Hydro-Quebec, as we all know, has a flat pricing of 7 cents per kilowatt. And this is like a simulation for the energy profile for a generic agent. And we tested the economical validity of the COC architecture by considering the generic agent in the previous simulation operating in standalone, where he's just interacting with the grid provider. And the second case where we have one RPC, and he is participating in that residential prosumer cluster. And we shown that the energy bill that generic house has like a significant reduction of 29% when he's participating in the COC compared to the 16% where we only consider one RPC. So and kind of in an intuitive way, what happens is like we are using our local resources to the best of its ability, and we're using our global potential to the best of its ability. That's why we reach kind of this reduction. As for the scalability and security, in this framework, we are solving the problem in a decentralized way, where we don't have a centralized unit that is trying to have full control over your appliances. You are trying to do it in a super decentralized way. That's like with a limited amount of communication, we were able to reach equilibrium. In addition, that the algorithm can be solved in offline, meaning that you can find your convergent distributions offline, and then you can feed it when the system is running. And so instead of working with all possible trajectories, you just like in real time, you solve your the whole trajectories offline, and then you have your trajectory and you just feed it to the system and you find your optimal controls. And this design guarantees scalability. Thus, we can say that the approach has a potential to be used for large residential energy networks, such as the one that we considered. Here, we're still assuming that we are dealing with a super dense network where we have a large number of connections between the nodes. So houses have plenty of connection in their neighbor, and the aggregators have plenty of connections as well. So in conclusion, we presented a decentralized optimization framework for the optimal energy trading in large-scale residential prosumer network using Graphon mean field game theory. The approach aims to partition the distribution grid into residential prosumer cluster, each managed by an aggregator. The aggregator is here only to mediate the interactions. We don't have any centralized authority. Everyone is doing it in a super decentralized way. The GMFG formulation enables scalable and privacy preserving coordination by modeling local and global interaction through an electrical distance weighted Graphon kernel. We presented theoretical and numerical analysis that established the existence and uniqueness of the equilibrium. And this work is available if you would like to read more on Cahiers de GERAD, and it's submitted to PSCC. For future extension, what we're trying now is to consider the more realistic network where we have a sparse network, something similar to the IEEE 8500, where we don't necessarily need to have a super dense assumption to begin with. We can use sparse. We can use Graphoxin-based mean field game theory, which models the sparse network. In addition, we're trying to extend this problem to have the grid provider as a player instead of just like having a fixed price or flat price. We're trying to formulate this problem to deal with a more dynamical pricing in a way that he is kind of the major player, and we're trying to, and his decision kind of affect everyone individually, and our aggregate effect affect the decision of the grid provider. Those are the list of references. Thank you.
Thank you very much, Mohamad.